Hi folks, welcome back. Today we're going to talk about two different kinds of parent functions. We're going to discuss the cubic parent function and something called the cube root parent function. But before we do that, I want to kind of review a few things with you from before the winter break. So before the winter break, our conversations were very heavily centered on inverses and how to identify inverses. And graphically, we talked about a way to identify if two functions were inverses of each other. So we discussed that quadratic parent function. Remember that the quadratic parent function was a parabola with vertex 0, 0, and if you followed the quadratic pattern, you could plot the rest of the points on the parabola. So every time you go over 1, you go up an odd number. So over 1 up 1, over 1 up 3, over 1 up 5, and so on. So this was the quadratic parent function. And we also discussed the square root parent function. Now the square root parent function is kind of half of a horizontal parabola. We don't include the negative part because otherwise it would fail the vertical line test and it would no longer be a function. We would have repeating x values. So we only use the top or positive part of that horizontal parabola for the square root parent function. Now, I'm showing you the line y equals x because this is how we discussed inverses graphically. In order to verify that two functions were inverses, we needed to make sure that they were reflections of each other over the line y equals x. So you should be able to take a point, count diagonally to the line y equals x, and count the same distance diagonally past the line y equals x. And we should be able to do that with all of our points from the parabola, 1, 2, 3, to the square root parent function, 1, 2, 3. So these are indeed inverses of each other. Now, I'm going to take these away. I'm going to leave the line y equals x there because we're going to use it later. And I'm going to move to the cubic parent function. Now, the cubic parent function, the equation for it, let me see if I can get my pen here. There we go. The equation for the cubic parent function is y equals x cubed, the most basic equation with cubing the variable x. Now, if you're creating a table, I've already provided several x values for you, and in order to figure out the y values, y is equal to the x value cubed. So here, if x is -3, then I'm going to take -3, and I'm going to cube it. I'm going to multiply it by itself 3 times. -3 times -3 is 9, and -3 times 9 is -27. Notice how the sign from the x to the y value is preserved. They have the same signs. So that is going to be kind of important, especially whenever we graph. So I'm going to do one more for you, and then I'm going to give you time to pause the video and finish the processes and finish finding the y values for that cubic parent function. So again, y is equal to x cubed. So if I take x and I cube it, not just the 2, but the -2. -2 times -2 is 4, and another -2 times 4 is -8. Again, notice that the symbol, the sign, is preserved. Both x and y are negative. So what I'd like for you to do right now is pause your video and try to find the rest of the y values using the same process. Take x and cube it. Pause your video. So you should have the following y values. Check yours to make sure that they are what mine are. And this table creates a set of ordered pairs. So every x value, I should have thought about that a little bit better. I'm not sure you can see that very well. Every x value, there we go, is paired with a y value. So the first ordered pair is -3, -27. The next one is -2, -8, and so on. So what I'd like for you to do is take the time to plot the points that are visible on this graph. Now, obviously, -3, -27 is not going to be something we can plot on this graph. Now, I do know that it's all the way down here somewhere, but because it doesn't fit on my graph, I'm not going to bother with it. But take some time to plot those points. So I'm going to plot them in real time, and then you can plot yours as well. So -2, -1, 2, 3, 4, 5, 6, 7, 8. -1, -1, 0, 0. There we go, 1, 1. It's hard to plot. There we go, come on, it's not letting me write. There we go, 1, 1, 2, 8, 1, 2, 3, 4, 5, 6, 7, 8. And then 3, 27 is not something we can plot. So I'm going to go ahead and fill in my graph. And it looks like a giant squiggle, kind of like that. Okay. So this is my graph. My key attributes of this graph, we're going to see that a lot of the key attributes from other parent functions occur here as well. So the first one we're going to discuss is the vertex. Now the vertex typically refers to the turning point. And in our graph here, our turning point is actually kind of an inflection point. It's where my graph stops curving up and starts curving under. So it changes concavity. Instead of concave this way, it changes concavity this way. So my vertex is 0, 0. And you might want to relabel this the turning point. Notice that most of the parent functions that we've discussed in the past, if it has a vertex, then its vertex is at the origin. The x-intercept, also 0, 0. The y-intercept, you guessed it, the origin again. The domain, well, if I go from the left boundary to the right boundary, maybe this is a good time for the green. My left boundary, I don't have a boundary because I have an arrow, so that's -infinity. And my right boundary, I don't have a boundary because I have an arrow, that's +infinity. So whenever I write my domain, that's all real numbers. Now I've got a similar situation for the range. From bottom to top, there's arrows. So for the range, again, all real numbers. Now this new thing that we're going to talk about, there's one more thing we need to discuss, is called end behavior. End behavior. So end behavior. And it is exactly what it sounds like, the behavior that's at the end of the graph. So we've got two end behaviors that we're going to discuss. The first one is as x goes to -infinity. As x approaches or goes to -infinity, a lot of times this arrow is going to be said approaches. So as x approaches -infinity, what direction are we going? Well, that means we're going this way. So as the x values go this way, what's happening to the graph? What's happening to the y values? They're going what? Down. Are they ever stopping? No, they keep going down, down, down. So as x approaches -infinity, y also approaches -infinity. So as x's go to the left, y's go down. That's what's happening. The other end behavior is the other end of the graph. So as x goes to the right side now, to +infinity, what is y going to? So let's look at our graph. As as x goes to the right and goes to +infinity, well, that's this. So what's happening here? All the y values are going up. So what direction is that? Towards +infinity. So as the graph goes left, it's going down. As the graph goes right, it's going up. And the way we say that is that the end behavior says that as x approaches -infinity, y approaches -infinity. And as x approaches +infinity, y approaches +infinity. So this is the cubic parent function. And the reason that we discuss the cubic parent function and the cube root parent function in the same day is because they're connected. So let me go ahead and get my marking tool here. So here is the cube root parent function. the simplest function that you can have with the cube root of a variable. Remember that if you just have the radical sign, that's the square root, but sometimes you can have the cube root. That means that what you're doing is you're breaking this up, this number, this radicand, into 3 numbers that multiply by each other to give you x. So I've given you a list of x values. I'm going to ask you to calculate the y values using the process. I'm going to do the first 2 for you. So remember that if you're given x, y is equal to the cube root of x. So here it's equal to the cube root of negative 27. So what times itself 3 times equals negative 27? Well, it's going to have to be a negative number. And 3 times 3 times 3 is 27. So this is negative 3. Let's do the next one. The cube root of negative 8 is negative something. Well, what times itself 3 times is 8? That would be 2. 2 times 2 times 2 is 8. So I'm going to give you a moment to pause, fill in the rest of the process columns, fill in the rest of the y values, and be ready to plot your ordered pairs. So pause and fill in that table. So check your process column, check your y values with mine. I've gone ahead and written all of the ordered pairs for x and y, so if you want to, you can write yours as well. Sometimes it makes it easier to graph. I know that I can't graph anything with a positive or negative 27 because that's going to be way off of my graph, but I can kind of get an idea for where it is. So negative 27 comma negative 3 is somewhere over here. I don't know where, but somewhere. Negative 8. 1, 2, 3, 4, 5, 6, 7, 8, and negative 2, that's right here. Negative 1, 0, 0, 1, 1, 2, 8, 2, 3, 4, 5, 6, 7, 8, and then 3, 27, all the way over here somewhere. So your graph looks like that. Very closely related to the cubic parent function. So graph yours, connect them, looks like a big squiggle. All right, so we're going to talk about the vertex or turning point. We're going to talk about the x-intercept, the y-intercept. We're going to talk about the domain and the range. And then we also talk about that new concept of end behavior. So there will be 2 end behaviors, one as x goes to the left and approaches negative infinity, and one as x goes to the right and approaches infinity. So let's talk about these. Vertex. Where is the turning point of this parent function? Well, it's right in the center, just like it was in the last one. It's at 0, 0. X-intercept, 0, 0. Y-intercept, also 0, 0. What about the domain from left to right? We've got arrows on the left, arrows on the right. So if it extends to infinity in both directions, that's considered all the real numbers for the domain. As it extends left and right, it's also going down and going up. Slowly, but it is. So the range is also all real numbers, negative infinity to infinity. So let's look at this end behavior. Let's talk first about as x approaches negative infinity. So as the x values radiating from the vertex go to the left and approach negative infinity, what's happening to the graph? It's steadily going down, right? It's going left, but it's also going down. So that means that the y values are decreasing and they're approaching what? All the way down at the bottom, if you keep going, that's negative infinity. Your y values are approaching negative infinity. What about as x goes to the right? Radiating from the vertex as x approaches positive infinity, What's happening to the graph? Slowly it's going up. The y values are getting bigger. So as x approaches infinity, y is approaching positive infinity as well. It's going up. So hopefully you've been able to kind of follow how to create those tables, how to create the graphs and these key attributes. The last thing I want to do before we end this video is to show you the cubic parent function. And I can't write a cube root in here, so I went ahead and put x to the power of 1/3, which is really the cube root of x. It means the same thing. So I wanted to show you both of these together. Can you make some kind of conclusion about the relationship between the red cubic parent function and the green cube root parent function? What's their relationship? What are they to each other? One, two, three. 1, 2, 3. Same distance, meeting here, meeting here, meeting here. They're reflections of each other over the line y equals x, which means that not only are they parent functions, but they are also inverses of each other. Just like the square root and the square parent function, we've got the cube root and the cubic parent function as inverses of each other.